much. I'm glad to see some people in the audience, given that we have semester and lunch break and everything else. It's my pleasure to introduce our visitor, Panos Singoulis, from the University of Nottingham. He is in his background civil engineer, which I will generously not acknowledge, but more focus on his experiences in surveying. His talk and his work is very much related to deformation monitoring, deformation analysis, core domain of engineering or precision surveying. And I'm glad to have you here. Panos, over to you.
Thank you very much for the introduction. Thank you for coming. Thank you for the invitation. What I want to give is an overview of my research, how I started, what I have done in the past, what I'm doing currently, and some ideas of what I'm planning to do in the future. From the beginning, when I started studying civil engineering, I wanted to do always something different from what was happening at the time. I'm coming from Greece, so civil engineering basically means you're a structural engineer, and your aim is to start building and start designing buildings. And I wanted to do something different. And when I studied back in end of 90s, beginning of 2000, I found, okay, what is more modern, what's more attractive at the moment? And then I realized that, okay, there's this idea, well, there was an idea of monitoring structures, but it's being more introduced in the surveying field. So, a few words about me. As I said, I studied civil engineering in the University of Patras in Greece, where I continued for my MSc, and finally I had my PhD degree there, and I investigated the potential of GPS and robotic total station for monitoring oscillations of rigid structures. When I finished, I became an associate, teaching research associate and teaching associate of the Department of Engineering Surveying at the Athens University of Applied Sciences. And then, when the crisis started in Greece, I decided to move on. So I moved to Switzerland, in ETH Zurich, where I shifted a little bit my research to geohazards and specifically to monitoring seismology, monitoring earthquakes using high GPS networks data. And currently, I'm assistant professor in geospatial engineering at the Edmonton Special Institute in Nottingham. So I said before, when I was studying, I was trying to find what are the challenges, what's challenging, what is new. And I realized that the major civil engineering structures become more challenging. So we're looking for longer long-span bridges.
Please reduce the volume of batteries. I see. You might do batteries in the mobile thing.
Switch it off.
Okay. So, where I was, long-span bridges becoming longer, high-rise buildings, they become taller. We're looking for tunnels which are longer, more deeper into the ground. So the conditions are more challenging. So there is demand not only monitoring during the period of the construction, but also after the construction, during the maintenance period, to be safe, to have safe operation, and most crucial is also the existing old infrastructure. There are long-span bridges designed in 50s, 60s for different conditions, for different loading conditions. So we have recent, for example, the failure of the bridge in Genoa last July, which, however, is not that often. The main problem is not that for civil engineering. I believe main problem is when you have problems in the operation, like what we had in Fort Road Bridge in the UK, which they had to close the bridge for a couple of days, and they estimated that the loss was more than £500,000. So the challenge is how to improve the operation, the maintenance of the infrastructure in order not to have problems like that. Other issues, for example, when on the opening day of Millennium Bridge in London, they haven't thought what would be the consequences of the pedestrian bridge interaction. So they realized that, okay, the bridge was not stiff enough, and as the people were crossing the bridge, it starts vibrating more and more. So they stopped it, they closed the bridge for a period, they made it more stiff, and then they opened again. And other problems is the geohazards. As I said before, earthquakes, volcanoes, tsunamis, they're always a problem. So there is a demand also to monitor, to develop early warning systems in order to limit the impact of these geohazards in structures. So monitoring of structures, it's something known in civil engineering. We're following mechanical engineering, and it is something known based on the traditional techniques that they were applied at the beginning, using accelerometers, strain gauges, and techniques like that. Always, though, the problem with these techniques is that we cannot determine what is the displacement, especially for very, very low response, very low frequency responses. So the introduction, this is when the GPS was introduced as a tool to monitor, to measure what is the displacement of the structures. Our first application was the monitoring of Calgary Tower in 1997, where even at that time, by using only L1 frequency, they managed to estimate roughly the amplitude of the response of the tower, which was about 2 to 3 centimeters, and estimate also the main motor frequency. Since then, there were made also more structural monitoring projects, mainly for bridge for bridge structure, for bridge monitoring, with using GPS. Also, at the same time, in about 2005, 2004, and early of 2000, there were a robotic total station was introduced, and with the capacity of monitoring a moving target automatically, thanks to this robotic function, became possible the monitoring of a moving structure. So, here you can see a robotic total station, how it's moving and it's following, it's recording the motion of this target, this prism. So some of the challenges which I was facing when I became a PhD student was some of the questions were, how much accurate are those techniques, GPS and robotic total station? How to improve their performance? How to make it even more precise? How to limit their errors, which is a problem especially for GPS, and how to use GPS or RTS measurements to relate the bridge response with the loading. So my first steps in research when I did my PhD was focused basically on experimental assessment of GPS and RTS, try to find what is the capacity, what are the limitations of GPS and RTS in monitoring dynamic motions, how to develop some methods to improve their performance, and how to assess these techniques in real applications. There have been done until that time, so beginning of 2000, measurements or investigations in assessing the GPS accuracy, but all of them they were focusing on frequencies below 1 Hz and mainly in displacement more than a few centimeters. So my aim was to focus in high frequencies, even up to 4 Hz, and amplitude even less than 1 centimeter. And it was based on a shaking, not shaking table, but a shaking device, where I had installed GPS and reflectors, so I was monitoring the oscillation for different frequencies by using GPS and robotic total station at the same time. So you can see here, yeah, that is me. And so you can see here some different scenarios, oscillation scenarios for different frequencies and different placements. So, as I said, the first challenge was how to determine the accuracy of GPS and RTS. GPS proved to be very accurate in monitoring the waveform, actually, of the motion. So we were able to define frequencies even up to 4 Hz. So GPS was proved to be very accurate in defining the waveform. However, it was not that accurate to define the amplitude of the oscillation, especially if it was less than 1 centimeter. And basically, this means that the noise which is introduced in the data was masking the correct amplitude. The RTS, on the other hand, proved to be accurate in measuring the amplitude of the oscillation. However, the main limitation was that the sampling rate was not like 10 Hz, how was the nominal value, but apparently it was less. It was between 5 to 7 Hz for this specific robotic total station, and this led actually not to record precise the cycles of the oscillation. So even though we could identify correctly the amplitude, the estimation of frequency was not that clear. It was more noise than it was with GPS. So at that time, we realized that, okay, GPS and RTS, actually, they're both accurate methods to use them, and actually they have supplementary performance. So with GPS, you can estimate accurately the frequency, even up to 4 Hz. With RTS, you can estimate accuracy the displacement, the amplitude of the oscillation. The main limitation for RTS is when the velocity of the motion becomes large, so large frequencies for large amplitude. When the GPS, the main limitation was when the amplitude becomes very small, like let's say like 5 millimeters. So in order to improve their performance, I was starting to finding ways to improve the estimation of the amplitude of the oscillation. So based on these experiments, I developed a method to mitigate the problems and reduce the impact of the errors in the estimation of the amplitude. So what we did, after filtering the data and isolating the peaks of the oscillations, we knew that, okay, these peaks, they have errors, even if they are GPS or RTS measurements. So what we need to do is to calibrate in a way the measurements and to have the correct mean average. So based on this computer-controlled experiments, we found what should be this factor, which we should multiply this amplitude defined by these measurements in order to get the correct measurements, based on the experiments that we did. And this is how we define this correction factor K, which depends on the frequency of the motion. Of course, this K factor is different for different GPS receiver or different RTS sensor instrument. But of course, the methodology this can be applied for any sensor. The third challenge, as I said, was to try to limit the impact of some error sources. For GPS especially, the main problem in instruction monitoring is the multipath error. The multipath impact is, or the multipath effect is when the GPS antenna is not receiving directly the signal from the satellite, but apart from that, it is receiving also reflection of the GPS signal from surrounding objects. Then the problem is that this multipath effect introduces error in the positioning, estimation of the positioning, and this is one of the main error sources for structural monitoring using GPS. So this was the main challenge when we did monitoring of Gorgopotamous Bridge, it's a railway bridge, where what we have is this situation, that the train is passing and the GPS, which is installed on the railway, on the handrail, at the side, it has strong multipath effect due to the reflection on the wagons. And the problem also with this bridge is that the main challenge, another challenge is that we didn't have any idea what should be the motor frequency. We had an estimation that, okay, it should be something above 3 Hertz, but however, we didn't know because this bridge was destroyed and rebuilt twice during World War II. So what we did GPS measurements, GPS and robotic total station measurements. So here you can see one point on the bridge. And the aim was to find what is the main response, what is the response to the bridge when the trains are passing, because from the railway service they were complaining that the those were operating the trains were complaining that when they were passing from the bridge they had to reduce significantly the speed of the train. So again, we saw that the main problem will be the multipath, so how we can reduce the multipath effect. What we did is that we tried to identify what are the main frequencies in GPS and RTS measurements, because we believe that both GPS and RTS should record correctly the waveform of the response, but the GPS would have significant noise level, significant increased noise level due to the multipath effect. So we identified which frequencies are common, and then what we did, we said, okay, these are the same frequencies, so this means that they have same waveform. So we know that the GPS measurements they record more precisely, more in details, let's say, the waveform. So we try to calibrate the GPS measurements again based on the amplitude of the robotic total station. Because if you can see here, the response based on the GPS measurements, it was amplified, reaching even up to 30 millimeters, which was beyond what was expected for that type of bridge, when in reality was like 3-4 millimeters. So we used the robotic total station measurements to calibrate the GPS measurements and to estimate precisely what is the waveform. And the fourth challenge was to correlate the weight, the trains which are passing from a bridge with the response of the bridge. So for that purpose, because we were more interested to see what is the amplitude of the response, we focused on robotic total station measurements where the amplitude is more accurate, and we saw that depending on what train is passing, not only the amplitude or not only the waveform is changing, but also the amplitude was significantly dependent on that. So we can see here a case where there is just noise, there is no train passing. Here there is one wagon service train which is passing, and we can see here the response in the middle. And here we can see the response of 8 wagons, freight train of consist of 8 wagons when it was passing from the main span of the bridge. During my PhD, apart from the application of my study in GPS monitoring and RTS monitoring structures, I had also the opportunity to be involved in some projects in geohazards, monitoring geohazards, and specifically monitoring the volcano of Santorini. This was done in a collaboration between the University of Patras and Georgia Tech. So, in the beginning, I was involved in measurements, in monitoring of Santorini volcano, which was based on EDM measurements, electromagnetic distance measurements, between 1999 and 2004. And basically what we were doing is that we were measuring the distance of the specific of the baseline between control points, which were connecting the center of the caldera with points in the perimeter of the caldera. So we're monitoring the changes in the baselines, and we found that basically for this period, the northern part of the caldera, there is some displacement, there is some deformation at that point. And based on the analysis of the changes on the baseline of these 6 stations, we could identify what is the strain ellipse, the tensor of the strain, how it's being deformed, and where there is also a potential magma source. But at the same time, we're trying to move from EDM measurements, which was old function technique, to something more permanent. So we installed GPS permanent network consisted of 5 stations. And we had also every year a GPS campaign. The interesting period started in 2011. In January of 2011, we had a sequence of seismic events, and also there was a displacement which was accumulating. So in 2011, we had 600 almost earthquakes, and the displacement of this station Novi here was an indication is that this station moved to the east by 6 centimeters in 1 year. So there was a clear, clear expansion of the, let's say, of the caldera, which was an indication that the magma source is coming up. Based on the measurements of the GPS, of the permanent GPS stations, at that period of 2011, as we can see, they're increasing. So the network is expanding. We estimated the deformation, which is the red arrows here, in the horizontal and vertical plane. And based on these measurements and applying it in a multi-source model, we were able to identify what is the source and how deep it is, about 4 kilometers. So this happened in 2011, and this is when I decided that it's time to go and impart the opportunity to join Geodesy Geodynamics group in ETH, where I collaborated with seismologists and geodesists in a project where the aim was to evaluate what is the potential of high-rate GPS networks for seismology and early warning systems. So the main objectives were to evaluate the consistency of GPS seismic data, to evaluate the performance of the GPS data in defining the characteristics of the earthquake, and developing of an early warning system for GPS networks. And the test bed, let's say, was Tohoku earthquake of 2011, magnitude 9. This is the deformation as it is recorded from the GPS network. The arrows are the horizontal, and the color scale is the vertical deformation. One more time. The epicenter of the earthquake is here. So, come on. The epicenter is here. So the amplitude, the horizontal displacement reached or exceeded the 6 meters. So it was a huge earthquake. So working on this data, seismic data and GPS, we're starting by estimating, by investigating what is the correlation, what is the consistency between GPS and seismic data. Because seismic data is what is being used until now. Can GPS contribute to that? Is it accurate and consistent enough with GPS, with seismic data to be those two to be combined? So we estimate displacement, velocity, and acceleration from GPS and seismic data, and for the periods which we could work with, because the GPS data were 1 Hz, we split them in 2 periods, between 1 and 10 seconds, and 10 and 100 seconds. So we worked on different period bands, and we saw that these two on top are 2 seismic networks, and this one on bottom is GPS. So we found out that both GPS and seismic data are consistent. GPS, of course, it's more accurate in displacement, and from the seismic data, you're getting better estimation of acceleration. And also, we worked on there to see how adequate is GPS in monitoring earthquakes. So at that time, GPS could record even up to 100 Hz. Do we need 100 Hz? So, because the higher sampling rate you have, the more data, the more noise you introduce in your data on GPS. So based on stochastic models of earthquakes from Switzerland and Japan, which means earthquakes of magnitude 5 up to magnitude 8, 9, we found out, and based on the GPS noise level, we found out that GPS doesn't need to exceed 5 Hz, because if you have 10 Hz or 20 Hz, the only thing that you can have is that you're introducing more noise in your data. Also, on the other hand, we found out for the earthquakes more than of magnitude more than 7, you can estimate relatively accurate the maximum ground velocity or maximum ground acceleration, even up to 78%. And I'm focusing on PGV because PGV is one of the parameters which is assessed right after or during the earthquake in order to estimate the significance of the event. And the last thing, as I said, the aim was to develop an early warning algorithm to analyze GPS and not only data. So this, in seismology, usually they have a very basic approach saying that, okay, we have the seismic data, we estimate what is the noise level, and whenever we have an indication exceeding the noise level, then this means it's a seismic event. They use that because they know that, okay, seismic data are very precise. But with GPS, it's not that precise. So the algorithm has two parts. In the first part, we're estimating what is the noise level of each station separately, and we identify whether we will have a measurement which exceeds this noise level. If it is an outlier and it happens just one epoch, then okay, this is characterized as an outlier and it is rejected. But if this continues happening, then we check what's happening in other stations, neighboring stations. Do we have events of like that, displacement similar to that in a surrounding area in a specific time period, which could means that, okay, this is a seismic event. If yes, then this means that it's a seismic event. If it's not, we don't observe any other, something like that in other stations, then this means that, or this anomaly, it's a specific anomaly. So again, this is how the earthquake was detected from two seismic data and from GPS network. From two seismic networks and GPS network. Still, the GPS is not that fast as the other techniques, as the seismic data, but still is consistent enough. This means that it can contribute. So, current research, the new challenges which I faced. When I moved in the University of Nottingham, I had to adapt. They don't have earthquakes in the UK, so I had to adapt to different research fields. So, the first question which I had was, can we exceed the limitations of GPS and the geodetic techniques in order to make it more competitive to other sensors, like accelerometers, for example? How can we use the geodetic data to analyze them? How we can improve the analysis of GPS data in order to provide useful information? How can we improve the analysis of GPS networks for geohazards and engineering monitoring projects? And finally, if we can enhance also the performance of low-cost sensors. Can we get something more? And we know that the low-cost GPS sensors, we can use them in our mobiles, we can use them for navigation, but can we use them, for example, for a more accurate estimation for monitoring projects? And more questions to come. So, when I arrived in Nottingham, I thought, okay, it's a good opportunity. Until then, we were using GPS mainly. But what about other satellite systems? At that time, okay, GLONASS was existing, it was used in the past. But what about BeiDou? What about Galileo, which is now actually it start being used? I thought, okay, we are using GPS, but if we use more satellite systems, can we improve the accuracy? Can we improve the performance for the monitoring projects? To investigate that, we did some zero baseline measurements in the UK and in China, so we could also include BeiDou, and we saw that GPS, okay, it's performing well, we know that, it's a well-established method, but for periods when GPS has problems, which could be related to the satellite constellation, the other satellite systems, GLONASS or Viridou, can be introduced, can be combined, improve the satellite constellation, and by this way improve also the accuracy. So here you can see this is the site in the UK, and you can see the correlation between the standard deviation of the measurements of the GPS and the dot value, which is indicator of the satellite constellation geometry. And this is for the horizontal and sorry, this is for GPS only, and this is for GPS and GLONASS. So we found that there is a clear correlation between the geometry and the accuracy. And if you have problem with the geometry and GPS, this is when you can use GLONASS or Viridou, depending on where you are, to improve the accuracy of GPS. And then we saw that for zero baseline, which is ideal case, let's see what's happening in real application. So we focus on 7 breeds, this in the UK, and we did monitoring of these breeds for a couple of days, and we tried to see what is the impact of the satellite, of other satellite systems, and how we can improve the accuracy of GPS. So here we can see a representative case where we can see how it is increased the dot value of the vertical component, which means that the satellite constellation, the geometry of the satellite constellation of GPS is getting bad, let's say. While for the GPS and GLONASS, the green one is stable, which means that the satellite constellation is fairly good. And then we observe what's happening in the estimation of the response of the breeds. With the blue one, you can see the GPS estimation, which is having significant, much larger amplitude than the green one. And at that side, you can see the GPS constellation and the GPS and GLONASS constellation. So yeah, from here, and also some other independent measurements we used with robotic totalization, we saw that, okay, the green one is the accurate one, so the GPS and GLONASS is the accurate measurement and not the GPS. So we saw that how the GLONASS or the multi-GNSS solution can improve the monitoring for cases like that. Another challenge, how to analyze monitoring data. And this is not only for geodetic data, this is for any type of data. I mean, it's what we call now the big data challenge. We have a lot of data, and we need to manage them and to maintain them, and how we are going to analyze them. So this is from the GeoSHM project, where I'm with 2 colleagues from University of Nottingham, Dr. Meng and Dr. Owen, and we're developing a monitoring system for long-span bridges. And the main aim is to combine GPS, accelerometers, inclinometers, anemometers, thermometers, sensors, which they can monitor what is the input, the temperature and the wind load, and what is the output, the response of the bridge. This is done in real time, and the analysis of the data, they're being done in 10 minutes intervals. So we are estimating the response for every 10 minutes. This is a print screen from the interface that we have developed for Fort Road Bridge. Yes, sorry, I forgot to say that Fort Road Bridge is the testbed, let's say, for this monitoring project in Scotland. This is the Fort Road Bridge in Scotland. And this is the interface where we can see in real time what is the response along the bridge, lateral to the bridge, vertical to the axis of the bridge, to the main axis of the bridge, and also we can see at the same time what is the wind load, the temperature, and other characteristics measured by the sensors. So as I said, we analyze the data in 10 minutes intervals. So we estimate what is the mean response for 10 minutes, what is the standard deviation for every 10 minutes, the wind load, the temperature, and all this. And we're trying to find what is the pattern of the bridge response for these 10 minutes and to correlate the wind and the temperature with the response. So for example here, for a period of 3 weeks, sorry, one month, we estimate what is the mean average of the vertical response and the standard deviation. And we can see clearly that for the standard deviation, basically the standard deviation indicates what is the dynamic response of the bits. And we can see that during the week, the standard deviation, it is increased significantly relatively to the weekends, where we don't have, the traffic is not that much, so we don't have a lot of large standard deviation, which means that we don't have a lot of dynamic response in the vertical direction. While for the from the mean response, we're getting a daily, let's say, waveform, which indicates what is the impact of the temperature. Of course, it's not the same every day because the temperature is not the same every day. So it is not dependent on if it is weekday or weekend. But it's clear the daily cycle of the vertical mean response. On the lateral component, we can see that the standard deviation, it indicates basically the impact of the wind. And we can see here an event also the same, it's in the mean response of the lateral direction of the midspan. We can see here an event of very strong wind. Another challenge we are trying to develop, to investigate, is how to analyze GPS networks, the data of GPS networks. And I mainly focused on temporal analysis and spatial analysis. So I'm analyzing temporally the GPS data, means every station separately, and by using neural networks in order to model more accurately the GPS time series. And the spatial analysis, it is done epoch by epoch, and the main aim is to relate the GPS data from the entire network and to see how consistent they are, and if there is any, what's the correlation between the GPS stations, and if there is any anomaly at any station. And combined analysis is when I try to combine both of them. The aim of all these different approaches is to develop algorithms which can be used in order to identify anomalies in the GPS data, which could be related to geohazards, or could be could reveal site-specific anomalies. So first application is again, we try to apply this again in the earthquake of Tohoku-Oki, and we compare the temporal analysis, the spatial analysis, and combine with the existing algorithm which we developed back in Switzerland. And we saw that the spatial method is not very effective for this type of anomalies, while the temporal analysis proved to be the most efficient one. And the combined is coming the next. A second application is to see if we can, by analyzing GPS network data, identify anomalies in the IWV values. IWV is an integrated water vapor. This means that if you have a significant increase of integrated water vapor, means you have large quantities of water in the atmosphere, which means that probably we'll have large amount of rain. So what you can see here, probably it's not very clear, but what we can see here is that this is a day and a half, this period here. So by the red circles, you can identify anomalies detected by the spatial analysis. So this means here that there were some stations where the IWV values were increased significantly. And this happened in a period of 1.5 days. And when this disappeared, then it is not very clear, but there are some small dots here indicating what was the measurement in rain gauges. So it started raining, and then start getting larger and larger values from blue, which is here, is getting yellow and red, which means that we have large quantities of rain. And then not only this disappeared, but we had some increased values in the temporal analysis, which is the blue squares. And these are moving in front of the rain. So basically, the temporal analysis indicates where the rain is moving towards. And behind that, we can see with the values, with the dots, significant amount of rain. So by doing spatial and temporal analysis, we can identify, potentially, we can identify strong rain events. And the last one, challenge, is the multipath impact in GPS measurements. As I said before, multipath is an error for GPS instruction monitoring, it's a problem. However, GPS multipath is being used for applications in remote sensing. So by having, for a stable antenna and the same environment, the changes in multipath indicate changes in the multipath environment. So they're using multipath in order to retrieve the soil moisture, in order to model the tides, because the tide is changing, the multipath, the reflected signal will change, so the multipath effect will change. They're using it even for to monitor vegetation growth. There are many different studies in remote sensing using GPS multipath. So the main concept that we had was, the main idea was, what if we inverse this theory, this approach? So we have the same multipath environment for short time periods, let's say like 1 minute, we have the same multipath environment. The satellite for 1 minute, we can assume that is more or less stable at the same position, and we'll move the GPS antenna. We will have the same impact due to multipath, but this will come from the displacement of the antenna, not from the change in the multipath environment. So through the multipath, we can identify the motion of the antenna, because this change due to the motion of the antenna will be reflected in the changes of the multipath. So here we can see the signal-to-noise ratio signal. This is the displacement, and here we can see the signal-to-noise ratio, which expresses basically the multipath, the changes in multipath. And we can see the same oscillation like we have in the motion of the antenna. So we thought, okay, this is done in measurements. What if we try to apply that also in monitoring of structure, where multipath so far is a problem? What if we try to use it for our own benefit? So we can see here the GPS measurements, the time series. There is a lot of noise. There is a significantly increased low frequency noise. So we need to filter it and get this time series for a specific event. And this is after processing the GPS data, filtering the GPS data, and at the same time, we have this signal-to-noise ratio time series, which is without doing anything, the real data we are getting from signal-to-noise ratio. So we did spectral analysis of that, and we got the main motor frequency of the GPS, of the response of the bridge. By doing the spectral analysis of the signal-to-noise ratio data without doing anything with that, filtering or processing, we identified, by using the signal from 3 satellites only, we identified the main motor frequency as well. So, based on all this, some ideas for the future challenges and future questions. We saw, first of all, that so far multipath was always a problem, especially for monitoring and for navigation. But what if we try to use multipath for our benefit? What if we try to apply what I saw earlier and define and use multipath to track changes in the positioning solution? And think that this doesn't require any processing or any data analysis. It's just the data, and you need to develop models, and from here to identify what is the change in the positioning. And this will be important, first of all, again, for remote sensing applications, and potentially could be a very significant tool for applications in urban canyons, in urban environments, where this multipath is a big problem, and usually you're trying to find ways to mitigate it. But what if we try for short periods to use it to model, by using the signal-to-noise ratio, to use it to model changes in the positioning of the antenna. Then another idea is, as I saw, that we can use temporal spacing analysis to to improve the information that you can get from GPS time series and GPS products. For example, I saw before IWV values. It's not position solution, it's the product which you can still get from the GPS processing. What if we can use these techniques, these approaches, these algorithms, not only for the application for geohazards, but even in order to improve the operation of GPS networks. And of course, this is not only applied in GPS data, these techniques, this can be applied in every time and in any type of network. It could be applied in seismic networks, in tide gauges networks, and water systems. So there are methods which can be applied in any type of networks. And another challenge, which we start now to develop to investigate more closely, is how we can improve the performance of the low-cost GPS receivers or GNSS receivers. Because so far we were using only GPS, but now we start seeing that by using combined solutions, GPS and Galileo, it is improved even more the performance of low-cost GNSS receivers. And the main aim for that will be to focus, the main aim for that is to try to get as much as possible from low-cost GNSS receivers, which could make more commercial applicable the GNSS receivers, because the cost of dual frequency GNSS receivers, they can reach even 20, okay, yeah, here, I don't know the value because it's $1 trillion, but could be 20, 30,000 euros or pounds. So, and we use low-cost GNSS receivers, we drop significantly the cost, and we can use many more sensors, and we have, in that way, more precise and more detailed monitoring of structures. And another idea, another concept is to integrate data generated from low-cost sensors. For example, here, an attempt that we start applying is using smartphones and image processing. So to monitor the response of the bridge. So by using smartphones, still it's not very accurate. You have a lot of low frequency noise because of the drift, but still you can see here the displacement from robotic total station and the displacement from a smartphone. From a video which was recorded from a smartphone and the analysis of the images which were extracted, I think the sampling rate was 24 hertz or something like that. So still, by using a smartphone, this proved to be quite efficient. So what if in the future trying to reduce the cost by using low-cost sensors like that? Not smartphones, but cheap cameras, low-cost GNSS receivers, MEMS, which have been tested and are being used very broadly. And one of the biggest challenges, I believe, in academia, how to try to pass these challenges and try to engage to the students and try to engage them even more. What I'm trying to do in Nottingham, in one of the modules, it's for the AR module and MSc module, basically. One of the projects that the students are doing, group projects, is monitoring of the bridge. So we're going there every March, we're installing sensors for a day, we do measurements, they're processing the data, they're analyzing, at the end they do a very nice presentation. So basically, this is what they did this year by using the smartphones. So one of the big challenges is how to engage the students and how to make the courses, undergraduate or postgraduate courses, more challenging for the students and try to pass the research ideas and what is up to date now to them. Okay, and also I would like to, all this was made possible through my collaboration with people from University of Nottingham and Georgia Tech, from ETH in Zurich, and from the University of Nottingham, and of course, PhD students. Thank you for your attendance.
Thank you, Panos. Time for questions. Good.
Have you also ever considered the use of drones for the bridge monitoring and doing similar to the smartphones, and they can get like a full flight path around there?
Yes, this is something which we have thought. The problem, I don't know what are the regulations here. The problem is how to fly a drone over a bridge. So it's, as I said, I don't know what are the regulations here, but in the UK, they're quite strict. So you need to have a drone, you need to have a pilot for the drone which has, who is certified. We need to get permission to fly over bridges, so it's not that easy. Sometimes when you want to do that, and you don't really have fun, but say, okay, I have this, and you try to do it, it's getting so complicated, the progress behind that, then you say at the end, okay, give up. But yeah, no, this is a very good idea actually. For bridge monitoring, it's something which is being done actually. It's something which is been doing the last few years. You cannot investigate dynamic motion of bridge, but what you could do with drones is to try to identify potential problems, specific parts of the bridge by using special image processing, so you can identify cracks or things like that. So yes, this is something interesting, but it's a different approach. Usually, what we are doing is try to see what's the response of the bridge in real time, the dynamic response. This is, let's say, this could be a very good supplementary method to identify problems on bridge and try to relate them with the response of the bridge.
What's the typical frequency of like the spreadsheet shows the vibrations? Because with the smartphone camera, you take probably 1 picture per second or something like that. Is the frame rate sufficient?
No, you can get more than that. It is recording with this one here.
24 frames.
Yeah, 24. I think it was 24 frames per second in this one. And as far as I know, still you can even increase that one. I'm not an expert on that, but with the colleague which we tested that, you could even 24 hertz, something great. This one reads here, the motor frequency is 1.6 hertz.
Okay.
So, yeah.
Because I know in photogrammetry for certain types of vibration we use high-speed cameras.
Yeah.
1,000 frames per
Yeah.
second.
Yes. Yeah.
I guess
Of course. I mean, for very stiff structures, which is like I don't know, concrete or something like that. Yes. I mean, smartphones may not be ideal. I mean, as I said, smartphones. The problem is that it is drifting. It's not stable. So you need to have a better solution. But it seems that, or even smartphone with something cheap, you can use it for something. As I said, this is after. Yeah, it didn't show there what I had in the beginning because this is after filtering. But in the beginning, it was only this drifting. You need to remove the low frequency noise, and to get this oscillation.
For the case that the train was going on the bridge, that's a higher frequency.
Yeah, but yeah, at that time we didn't use it. We didn't have.
Even GPS that gives you like two measurements per second, I think, typically.
The GPS.
Yeah.
The GPS measurements from the GPS receivers.
Yeah.
What we used here in the railway bridge. Where is it? What we used here, the GPS, it was 10 hertz. 10 hertz. I mean, as I said, you can it's even up to 100 hertz. But in reality, what you are doing with 100, when you are increasing the GPS sampling rate, in reality, you are increasing the noise. It's what do you need? For earthquakes, we proved that you don't really need more than 5 hertz. You cannot really, because the radius is not that, and the displacement that you are getting, it's going to be, for more than 5 hertz, it's going to be very, very small, so we cannot really detect it with GPS. For structures, to be honest, what you can detect for displacement more than a few millimeters, it will be again 3-4 hertz, will correspond to frequency of 3-4 hertz. You don't really need 50 hertz. What you can get by having 50 hertz or even 100 hertz GPS data is that you have better resolution. So if you want to get information that you cannot really get it from 10 Hz, you can filter the data and then you have more chances to get information that maybe you're losing with 10 Hz, that's all. But it's not that you're getting high accuracy. The accuracy is worse actually. But you might be able, after filtering, to get some information that you're losing if you have lower sampling rate.
Martin.
I'm just wondering about some other applications you can come out from the analysis of the signatures it detects. So could you, for instance, detect whether which component of the response is from one source and another source? Let's say what we'll have here, we'll have a train station plus a lot of traffic around, and we have very sensitive instruments, for instance, a medical building across the street where they have a electron microscope. So saying, well, this is latent stuff from the trams and buses, and this is from the train when it passes. And maybe it passes too fast and breaks the rules and jiggles too much. Can you tell that it's not just the sum of two small things, but one has exceeded some?
Well, the difference between the trains and the buses and all the rest is, I believe the difference could be on the pattern of the formation. So, from the specifically for trains, you expect to have very deterministic pattern. That every axle of the train will have a big response like that, for the next one another response like that. So you will have very deterministic pattern based on what's the length of the train, based on what's the speed. So based on all that, you will be able to identify the frequencies which they will correspond to the response due to the train. So by this way, yes, the problem is when you have vehicles, when it's random. This is more complicated. For temperature, it's more straightforward. You know that there is a daily cycle, so it's relatively easy to identify. Also, for wind, you know what is the wind load, the direction. You know how you can correlate it. Actually, I have one slide, but it's not the best one. So this is from the Fort Road bits. What we tried to do was to use as input the temperature and the wind load, the wind speed, let's say, and as output the response of the bridge. And by training a neural network, the input was temperature and the wind load, and the output was the output was the response of the bridge. By training a neural network, it was possible. You can see the blue line is the maximum response that we were expecting. The green line is the minimum, and the blue line is the mean. So the mean response that we were expecting. So by this way, we can see that you can easily identify. This is the mean, and this is the standard deviation. So the mean response is due to the temperature. So it's relatively easy to identify the mean response of the bridge because it's strongly driven by the temperature, basically. The standard deviation, which is a combination of wind, traffic load, then it's getting more complicated, but then there you can identify what is the response due to the wind when you have days where you have strong wind and days where you don't have strong wind. So you can extract from there the information that you need. Okay, what is the impact of wind on the structure? Okay, the rest is from the traffic. So then you can train the neural network and you can define a model. What is the response due to the wind, due to the temperature, and the rest is due to the traffic. Now try to separate the type of the traffic. This is coming from a train or coming from vehicles. Then this is even more complicated, but I believe you can do that when you will investigate the different frequencies of the load. So this could be done by this way.
All right. As Greg indicates, time is up. If you have further questions, Panos is here for the next 2 days. Thank you all for coming and participating.